In this video, we are going to take a closer look at the AStar algorithm. So in this video, we'll not be implementing the algorithm, but we will be looking at how it works and the theory behind it. So we will actually learn about the building blocks of the algorithm before we actually start implementing it in the next video. So if you just stumble upon this video because you wanted to learn about AStar, well, then you can simply also follow along here. You don't need any specific project to be able to follow along. You should simply just follow along the video, and then you should be able to implement this in your own project as well. Because in the next video, I will be implementing it in the tower defense tutorial that I am creating right now. But you should also be able to follow along and apply everything to any game that you're creating with a grid-based movement system. So, as you can see, the algorithm is called AStar, and it's also written as A and a little asterisk as a star. It's an algorithm for calculating the shortest path from A to B, and it will always find the shortest path. The algorithm is very well known, and it's used in a lot of games, and it can be used in different structures, not only grid-based games as we are going to do here, but you can also use it in graphs and other things to find the shortest path. So the way that we are going to implement this is to divide our game map into a grid. So as you see here, we have a grid on it, and this grid looks a lot like what we have in the tower defense game at the moment. So if you're playing another game, or you're creating another game, then you should also somehow have your map divided into a grid. So on this grid, we need two things. We need a start position. So this is the place where our monsters spawn. Sorry about the phone noise. So this is the place where our monsters spawn. And we need a goal, and that's the portal that our monsters will be running to. So we need to be able to figure out a path from this point to this point here. So right now it should be fairly easy, and we could just use any move towards function in Unity to get the monster to move from here towards the goal here. But in lots of games, there are obstacles, and we will also have obstacles in our game. So we will have our towers blocking the way sometimes. So we define these grids or these tiles here in two different ways. And from now on, I'm going to refer to every single tile here as a node, because in the AStar algorithm, we can call every single tile a node we can move towards, or two. So these nodes can have two different states. They can be walkable, as any of the nodes around here, where there's no towers on them, and they can be unwalkable, which are the nodes with actually towers on them. So unwalkable can also be tiles with water on them, or cliffs on them, or mountains, or something like that. So anything you can't walk on in the game will be noted as, noticed as not walkable, unwalkable. So these are the two things we have: unwalkable with towers on them, walkable without towers. So the algorithm will look through all the nodes to find the shortest path from A to B. And in our case, it's from our start point, where our monsters spawn, to the goal. So there's a function that we need to use to calculate the shortest path. And it might look a little odd right now, but it's called f of x equals gx plus h of x. Okay, so basically we just need to look at these as f, g, and h. Okay, f, g, and h. And basically these will make a lot more sense now when I start to explain them one by one, because I know for a fact this looks very, very confusing right now. So let's try to make this a little less confusing, because every time I explain this to my students, show this to my students, they look a little confused, because this formula looks a little odd. So let's take a look at the basics of the algorithm. First of all, the algorithm works by using two lists: an open list, and the open list is a list of nodes that we need to take a closer look at some point. And then we have the closed list, and the closed list contains the nodes that we have examined. So this is nodes that have been on the open list, and these nodes can end up as a part of the final path. They will not for sure end up as a part of the final path, but they're candidates to being a part of the final path from start to goal. Okay, so we have open list with nodes we need to look at, closed list with nodes we have looked at and we have put aside because we think they might be a good choice to go through later. Okay, so G. Well, G is the cost of moving from start to this node. And horizontal moves and vertical moves cost 10 points and diagonal moves cost 14 points. So let's try to look at it. If we look at this here, we have our starting point and all these nodes around here are right next to start. So diagonal moves cost 14. So all the nodes that are diagonal, like these 14, 14, 14, 14, they have a G score of 14. But the nodes that are horizontal or vertical from the start node has a G score of 10, as you can see. So this is how we score it, right? So 14, diagonal, horizontal, vertical, 10. This should be fairly easy to understand. Okay, so how do we score the G score on the path towards the goal? Well, we take the G score of the parent and add the cost of the move to get to this specific node. Okay, so first of all, we start here at our starting point. It costs 14 to move diagonal to this node here. And then we move vertical to this one, which is 14 plus 10 is 24. Then we move horizontal to this one, and horizontal moves are 10, so it's 34. Then we move horizontal again, so 34 plus 10 is 44. And then we move what's called diagonal, not diagonal, vertical up here to add 10 again, so it's 54. So the G score along this road here will be 14, 24, 34, 44, and 54. And as you can see, we always take the parent, the node we are on at the before, and add whatever it costs to move from this node to the next node, right? So this is 0 because we start here, and move over here. That's 14 because the move is diagonal and it costs 14. And then move down 10, 10, 10, 10, and the end we end up with 54. And if we jumped up here, well, then it would be 64 instead because it costs 10 to move from here to here. Yeah. So that was the G score. That should be kind of understandable. So the H, well, the H is an estimated price for moving from any node in the grid to the actual goal. And it's often referred to as heuristics. And it's basically a guess of what it will cost to move from this node to the goal. All obstacles are ignored when we calculate H, and diagonal moves are also ignored, so we can only do horizontal and vertical moves here. And basically we take the length between the node and the goal and multiply that with 10. As you can see here, let's see, we have this node here, for example, 50. 10, 20, 30, 40, 50, right? So we have 1, 2, 3, 4, 5 nodes between. So this G score here is 50. Over here we have 10, 20, 30, 40. So it costs 40 to go here. From here it costs 20, 10, 20. This one is right next to the goal, so it's only 10. Same goes down here. It's only 10 to move from this one to this one. And again 50, 10, 20, 30, 40, 50. 30 here, 10, 20, 30, right? So that's how we calculate the H score here. So now we have the G and the H score calculated. And when we start creating the program for this, we'll just count how many fields are in between. There's 1, 2, 3 fields. So this score here will be 30 because 3 times 10. Yeah. So that's the H. Okay. So F was actually the value of G and H put together. So to calculate the F score, we simply calculate the G score, the H score, put them together, and then we have F. That's why it's called F equals G plus H, for example. that formula. So to calculate f on this one, we know it costs 14 to move from our starting position down here, because diagonal move. And we know it costs 30 because 10, 20, 30 to move up here. 14 plus 30 is 44. Down here, we know g is 24 because g score up here is 14. The g score down here would be 14 plus 10, which is 24. The h is 10, 20, 30, 40. 24 plus 40 is 64. Over here, 34. 24 plus 10 is 34. H is 30, 10, 20, 30. These two put together is 64. And over here we have 44, 34 plus 10, 44, and so on, 10, 20. And the same goes up here, right? 44 plus 10 is 54. H is 10. And 54 plus 10 is 64. So now we have actually calculated the f-score. And this f-score is very important for our algorithm. That's why we are actually going through this to figure out how we actually calculate this or put this together. And yeah, I know this is confusing right now. We have a lot of numbers, and what do we even need them for? Well, let's take a look at how the algorithm actually works so that we can see why we need these numbers here. Okay, so let's try to take a closer look at how the algorithm actually works. So the first thing we do when we start our search is to add the start node to the open list. And that's indicated with blue color here, right? So the start node is the node that the monster starts on. That's where he needs to go from. And the portal is where he needs to go. So we start by adding the node he's standing on to the open list. When we have done that, the next step is to take a closer look at all the neighbors around the node we are standing on, our current node. And all these neighbors are indicated with orange. And a neighbor is a node that is lying right next to the node we are looking at right now. So all these are neighbors. When we look at the neighbors, we will always ignore unwalkable nodes. So if the player would have started here, these three nodes here would be ignored because they are not walkable, they are unwalkable. Okay, so we look at these neighbors. These neighbors we just found will also be added to the open list. So now we just added all our neighbors to the open list. When we're done that, we will need to note or write down that the node we are standing on, in this case, which is start, is the parent for all these neighbors, because we used this node here to find all these neighbors. This is the node we were standing on at the moment when we were looking at the neighbors, or this is the node we were examining at least, when we found all these neighbors around it. So all these neighbors are now pointing towards this one, because this is the parent node to all these nodes around it. So the current node we are standing on needs to be moved to the closed list. So our start node in this case, which is our current node, is now moved from the open list to the closed list. That's why it's a darker blue now, because it's on the closed list. Okay, so the next thing we need to do is to score all our nodes. And as you can see here, we score the nodes as we just talked about before, right? We move down here. The G-score down here is 14 because it costs 14 to move from here to down here. And the H is 50 because it's 10, 20, 30, 40, 50 to move up here. And I just noticed I made a mistake here. I wrote 40 here. This is actually 50, so don't mind that. I'm not going to adjust this on every single picture because I made a mistake. So just keep in mind this 40 here should be 50. I'm sorry about that. And over here we have G10. Costs 10 to move from here to here, and H is 40, 10, 20, 30, 40, right? So F is 50 because 10 plus 40 is 50. Okay, so now you can see we just calculated all the F values for every single one of these, and now we need to use these values to continue our search towards our goal. So the next thing we do is to continue the search by selecting the node with the lowest F-score from the open list. Okay, so now it makes sense we have the F-score, right? Because we have calculated the F-score for every single node here. And now we need to go in the direction where the F-score is actually the lowest one. And in our case, the lowest F-score is 30. So we pick this one as the next current node. Now this is not our current node anymore. This one over here is our current node, because 10 plus 20 equals 30, which is way lower than the others. In some cases where you have two F-scores with the same amount, it's random which one it will pick. It will pick the one that would add it to the list first, for example. So it will take either one of the ways. As you can see here, in our case, we picked this road down here to the goal, but the road up here down here is actually also the same length. So it's just random which way it would pick when the length is exactly the same. Anyway, we have now figured out that this node here has a lower score than the rest of the nodes. So now we can continue, right? Yeah. The next thing we do is to take this node, because it's our current node, and move it from the open list to the closed list. So now it's also dark because we have it on the closed list. So it has a chance to become a part of our final path. The next thing we do, we examine all our neighbors and we ignore unwalkable nodes. Okay, so these neighbors here were already on the open list. So we can't add them to the open list again. That's why they have two colors at the same time. These nodes here are unwalkable, so we can't add them to the open list. So now we are examining all these neighbors we can see. Undiscovered neighbors will be added to the open list, which means if these towers wouldn't have been here, there would be 3 undiscovered neighbors we could add to the open list. Okay. So if we had some new neighbors, the current node we have here would be written down as parent for these neighbors here. So they would all point at this node here, if that was the case. But in this case, we don't have any new neighbors, so we can't make this one the parent of any of them, and we can't calculate the F, G, and H value of the new nodes here. But anyway, we have 4 nodes here, 4 neighbors that we already had on the open list. So what to do with them? We will need to check if the new current node here is a better parent than the original parent of all these neighbors here. And we know they have a parent already because they were already on the open list. In this case, we need to check if this one is a better parent, and we do so by checking the G-score. So they already have a G-score. So to check if this one is a better parent, we need to check or calculate a G-score of all these neighbors by going through this one as a parent, right? So right now, the G-score of this one up here is 14 because we go from here up here and the G-score is 14. If we go through this one, the G-score will be 20, and that's not lower than 14, which means that this one is still the best parent. This one over here will not be a good parent for this one because it has a higher G-score. So we don't need to change any relationships here. Let's say we have a situation where the G-score will be lower. Let's say the G-score would be 10 if we go through this one. Well, then we would need to check and recalculate the F-score on this one, and we will have to take the arrow here and point it on this one instead of pointing on this one, because this one would be the new parent. But in our case, this node here is a better parent for every single one of these neighbors here. Because as you can see, well, the new G-score would be 24 because we need to go out here. That's 10 plus 14. Well, the G-score down here is 24, which is higher than the original G-score of 10. Down here, the G-score is 14 because we can go from here down here. If we need to go through this one, it's 10 plus 10, which is 20, right? 10 plus 10. So in our case, this new node is not a better parent than the original one, so we don't need to do anything. Okay. When we have done that, we need to continue this search from step 7. And we need to continue that search until the open list is empty. If the open list is empty at any point, then there's no path available, and we can't find our goal, which means we can't move. Let's say, for example, if our portal here was framed in by towers, well, then we couldn't get to it. Then at some point our algorithm would empty the open list and we wouldn't be able to find anything. Or we will continue the search from step 7 until the goal is added to the closed list, which means we found our path. So if at any point our goal is added to the closed list, then we're done searching. And when we've done that, then we can find the actual path from start to goal by backtracking through the parents. That's why we have these parents, so we can figure out where we came from to find the path. Okay, so I am going to run through an example here for searching towards the portal. In this example, I am ignoring nodes that will not be a part of the final path. So the actual AStar algorithm will do a lot of more loops and take a little longer to find the goal, but I'm simply demonstrating here how to actually understand the algorithm and understand how it actually searches, right? In the end, I am going to show a real picture of how everything would look when we're done searching. Okay, so let's try to look at it. So we start from step 7. We just had this one as our current node, this one here. The next thing we need to do is to pick the node with the lowest F-score on the open list and move it to the closed list. Okay, so this one down here with 44 is the actual tile with the lowest F-score. So we pick this one and go this way. And as you can see, 44 is also up here. So it's simply random which one of these we would pick in this case. Okay, examine the neighbors, set the parents F, G, and H score. So we set the parent and we set F score, G score, and H score on the neighbors. As you can see down here, this one is also a neighbor, but it's actually ignored. And the reason we ignore it is because that if we would take a path down here, we would actually cross over this tower, right? Imagine if this tower, if we also had a tower here, then we would be able to pass through two towers. So to avoid some corner clipping in the game, we actually ignore this one down here, and we will also write code for that. So this one down here is not a neighbor at the moment. Okay, so we examine all our neighbors. These two are new neighbors. So this one is noted down as a parent for these two down here because we use this node to find them. The F and G and H score is calculated. The G is 14 plus 10 because we stand up here when we go down. H is 40, 10, 30, 10, 20, 30, 40, and that's 64. This one is the G score from going from here down here. 28, 14 plus 14 is 28. H is 50 because there's 5 in between here. And F is 78, right? So this one is also calculated. Okay. The next thing we need to do is to check, is this one a better parent than this one up here? Well, it's not because the G score is 10. If I go through, this one is 14 plus 10, which is 24. So the G score will not be lower. Okay. Then again, I pick the one with the lowest F score. As you can see right here, we pick 64. Up here, we have some with lower numbers than 64. And I'm simply ignoring those because I don't want to use all the calculations up here and show you everything. I'm just going to show you the correct path. But the actual algorithm would pick 44 up here and add these as neighbors. And then later it will jump back down here and start examining down here, jump back up here, examining up here, back down here and examine up here, jump back and forth. But not in this example, okay? So we pick, in this case, the neighbor with the lowest F score, which is 64, and we move it to the closed list. We again examine all our neighbors. We have 4 new neighbors here, and we calculate G, F, and H score on all of them, and we check if this one would be a better parent than the original one up here. Okay. So then again, we pick the node with the lowest F score on the open list, which is this one down here. And then we move it to the closed list, which we just did, right? Again, we check all neighbors. We ignore this one up here because there is a tower right here, so we can't pass through if there would be 2 towers, for example. And then we examine add 2 neighbors down here, and we check these 2 neighbors that we already had before, if this one would be a better parent. And we calculate F, G, and H score. Again, pick the one with the lowest F score on the open list and move it to the closed list. Again, we check all neighbors around it. We add the new neighbors to the open list, and we add the old neighbor, or check the old neighbor if this one is a better parent. And we calculate F scores on all of them, F, G, and H score on all of them. Then we take the one with the lowest F score, move it to the closed list, and then again we find all neighbors, And when we've done that, we do the same thing, check neighbors for values. We calculate all values and neighbors, check if these two has a better parent than this one. And when we have done that, we find the node with the lowest F-score on the closed list, open list. We pick that one. And now we actually found our goal because we just added our goal to the closed list, which means that we are done searching. When we are done searching, well, then we can actually use the backtracking here to find the actual path. As you can see, we noted our parents all the way because every time we found some neighbors, we added the current node as a parent for those. So we can actually say we are at our goal. Who was the parent? This was the parent. Who was the parent? Yeah, this one, this one, this one, this one. So you can see we can follow the arrows back to our start. So we can actually, we just found the path, and then we can return the whole path in a list to a monster here, so it knows which nodes it needs to walk to. Okay. So this was the simple way to find the path. If we would have used the right AStar algorithm, calculated up here, jump down here after, calculate some up here, it would look like this instead. Okay. So as you can see, there are lots of nodes on the closed lists that didn't become the actual end path or final path. You can see here we always made it here, but then we jumped down here after and we added our goal when we had this one as the current node, so we will go down here. We might as well have taken the upper road here, but in this case we didn't do so because it started going down here first, the algorithm. Okay, so that is how the AStar algorithm in basic or in general works. I hope it is kind of understandable how the value works and why we need to calculate them. In the next video, we will start writing the code for all this. So we will start adding all these values to the nodes so that we can use them for something in the game. And we'll implement one thing at a time. We will start looking at the neighbors one at a time. We will find all, calculate the values after, and so on. So I will do it step by step, so it makes it easier for you guys to understand. I will do it in relation to this video. So everything we did here step by step, we'll do exactly the same thing in the code so that you can look back and check it, how it actually works. So thank you very much for watching this video, and remember to share my videos if you like them. And don't forget, if you're not following my tutorial, you just came here for AStar tutorial, well then you should also be able to follow along here and get a better understanding of how everything works. So yeah, thank you very much for watching, and remember that InScope Studios is a community found page, so all your support is very important to me. You can support me in different ways. You can get this project or any of my other projects as a standalone product by clicking the bottom link, or you can support me on Patreon, where you can get every single project that I've ever created for my YouTube channel for $5 a month. So thank you very much for watching.